Ring is on. Shall we start, or we should wait for more to come? Okay, probably we can start. This is the course for AI or visual computing. Okay, so I'm today's presenter. My name is Jerry. Today I'm going to talk about animating expressive human faces. And I'll start by talking a bit about the backgrounds, which is the parametric 3D models. I will introduce to you the blend-ship models, the blend-ship characters, and the 3D morphable models, which is an unsupervised approach for getting the parameters to control the 3D faces. And I will also introduce a bit backgrounds, applications using the parametric 3D models. This includes facial reconstruction. Then we'll talk about the data-driven approaches that is used to animate expressive human faces. I'm sorry? Okay, how should I? Better? Yeah. Okay, so every light is on. I mean, every light is on, every switch is on. Okay. Yeah. Thank you. Okay. Okay. Next page. So a bit self-introduction. My name is Jerry. I am a second-year PhD student. My advisor is Professor Kapalia, which is the professor for this course. And my research interest includes virtual humans, animating virtual humans, faces, expressions, affects. And I'm also interested in building embodied conversational agents using like MetaHuman or Unity Unreal Engine framework. Another work I'm also interested in is the neural rendering. So if you have interest with regard to these topics, you can send me an email. Okay, so let's start by asking a few questions. What makes a human face? So for a human face, we have the bones. In the world of graphics, we call them the rigs or skeletons, if you're mentioning the bones for the body. We also have skins, which is something you can see from any person's face. And in the field of graphics, we call them the mesh or vertices. And the skin has colors. It has colors everywhere, like even the eyebrows can be represented as a color, a texture on the mesh. And we have other like components like hair. We have eyes. We can model it as a sphere inside the cavity here. We also have ears. We have teeth. When you open your mouth, you can show your teeth. And with these components, the next question is, how can we represent a face? Okay, and the intuitive idea is to use like you take a screenshot, take a photo of somebody, and you can represent the face in images, RGB images or pixels, or you can build a face, a virtual face in a virtual environment with like 3D vertices, the meshes, and the meshes has color. We call it textures. So these are the two common like representations of the face. And my next question is, how can we animate them? Okay, so if we're using the image-based representation, how can you animate a face in a video? You have to control the pixels, you have to control like the lightings, the reflections. And it turns out that if you're using 2D representations, it would be kind of difficult to animate them because there are so many pixels, and even the state-of-the-art like image generation model like StyleGAN 2 still suffer from this. So in terms of 3D vertices and textures, we actually have some parameters that we can use to control the faces. Okay, we can convert the high dimensional 3D vertices into a low dimensional space. So let's say we have expression 1, expression 2, and expression 10. We have these scales. You can roll it from the left to the right and it changes the scale. So I'll talk about this later. The outline of today's talk is as follows. We'll talk about the parametric face models, the two parametric face models. The first one, blend shape, which is commonly used in the industry for animation production. And the second one is 3D morphable model, which is commonly used in the area of research. We also talk about the applications using the parametric face model, which is the monocular face reconstruction. Then we'll talk about audio-driven face animation. So for parametric face models, we start by introducing to you the 3D face meshes. The mesh is actually like a collection of vertices or points on your face. So if you are to represent the face, you have to use lots of vertices to represent them. So you can look at this one-dimensional vector where we have the first vertex with x, y, z components, and the second vertex, the 3 components, the end vertex with the 3 components. And in order to control the face expression and animate the faces, we prefer to use a low-dimensional control space to animate them. So there is a linear mapping between the raw face vertices and our control space. And in general, we call them like the face, the vertices, or the raw vertices. We call the control space as weights, and we call every column of this transformation matrix as a blend shape. So from this equation, you can immediately think of the facial vertices as a linear combination of like the n blend shapes. Okay, so this is the basic idea of parametric 3D face model. Let's look at some examples. Okay. So this is the Flame 2020 3D morphable model. And there are several control space parameters, which we call weights. The weights can be as small as -2 and as large as 2. And you can see as I change the slider value, the expression changes. And if I change expression 2, some expression changes, I can also activate more than one expressions to create new faces. And also I have control over the jaw. I can open my mouth. I can kind of rotate, rotate my neck. And I also have some control over the size of the face identity. It's larger, it's shrinking. Is this okay? The face becomes bigger, shorter, and other stuff. So this is the basic idea of using parametric face model to represent a face in the 3D world. Okay, let's go back. Okay, so blend shape is one of these parametric face models. Actually, blend shapes are static poses of a character. So we can have weights that are limited between 0 and 1. We can take a look at this metahuman example. This character has like 300 more blend shapes. Among the 300 blend shapes, only 2 of them are activated, which is the eye blink left, and the eye look out right. So the eye looking out right. So it's actually another example of blending between like different expressions to create a distinct expression. And how are these blend shapes created? We can start from a neutral pose, assign it with weight 0. We then define a new pose and assign it with weight equals 1. So let's say we designed a new pose called eye blink left. So left eye is closed and weights equals 1. And for those weights that are between 0 and 1, let's say 0.5, is actually the interpolation of the 2 poses. Okay, so this is the basic idea of blend shape. So blend shapes are commonly used by artists or animators because blend shapes are created for reasons. They are semantic parametrizations. That means for a single parameter, we can control for specific semantics. Let's say we would like the character to open its mouth, to kind of smile, open the jaw, eyebrows goes up. And we can use those semantic parameters to create an animation or edit an animation. So take a look at this example. So these are like blend shape values along the time axis. So you can see as time goes to the right, some of them are activated, some of them are not. And these combinations of values creates the animation. Okay, so for a standard animation pipeline, in order to create an animation, we're gonna start by first sculpt the character that looks somehow like this. And then we create blend shapes. So for a industrial standard, at least 300 more blend shapes should be created. And once we have those blend shapes, in order to animate a face, we have to do keyframing. That means at some specific intervals, we assign that keyframe such that that keyframe, the face expression acts like what we need. And once we have those keyframes, we start to do smooth interpolation between the keyframes to create the animation. And all these 4 processes are manually created. So you can think of like the animation pipeline is kind of is an arduous work, it's time taking because you have to sculpt the character, create blend shapes, and put time into smoothing the interpolations. Okay, so those are for blend shapes. Then we're going to talk about another branch of parametric 3D models, which are 3D morphable models. We're going to start by scanning faces with our 3D sensors. We invite like hundreds of variety of people, do a static scan. They can have different expressions that are asked to do. These 3D faces are calibrated to face the front view. Some of the hollow areas are filled to create this face. And it turns out that there are more than 10,000 vertices for each face. In order to control and create new face and expressions, what we are doing is to do principal component analysis, which is an unsupervised dimensional reduction approach. So we can consider like the vertices as a one-dimensional vector with the first vertex x1, y1, z1, and these m vertex. And for the vertex, since we can have textures on it, every vertex has 3 RGB components. So you have a morphable model for the vertex positions, and you have another morphable model for the texture. Okay, so starting with the high dimensional like vertex vector, what we are doing is to do principal component analysis. We find the basis with the largest variance from the data distribution. And if you're familiar with like linear algebra, it turns out that principal component analysis is a process of singular value decomposition, where you decompose the face matrix as a diagonal times, an orthogonal matrix times a diagonal matrix times another orthogonal matrix. And the basic idea of principal component analysis is to keep the first few largest principal components and do a bit reconstruction so that we can have, let's say we have 10,000 vertices, an array with 10,000 dimension. We can reduce it to 500 principal components and use their corresponding eigenvectors to reconstruct from the low dimension space to the high dimension space. And it turns out that the first 500 principal components covers at least 90% of the variance of the data. So because this is an unsupervised process, we will later be using the 500 parameters to control our facial expressions control the face identity. So not just identity, not just like expressions, not just textures. We can also have like identity expressions and vertex positions blended in, entangled in a 3D scan. And we can use similar PCA-like approach and extend it to a bilinear model or multilinear model. So you can think of like, if this is a PCA model, actually the original face vertex is actually a weight times our low dimensional vector. But since we have like identity and expressions, we have the weight, the matrix becomes a tensor, and we have the two control space. Let's talk about some details using the Basel 2009 3D movable model. This is first ever created 3D movable model. So let's assume we have a set of vertices called S, represented by vertex XYZ, vertex 1 XYZ, vertex 2 XYZ. So this is a long high dimensional array. It's actually an average pose S0 plus the A identity, which is the like first principle axis times your weight. So take a look at this example. We have the average shape, which is this character. For the first principal component, if this is 5 sigma away from the mean, it actually becomes quite small. And if -5 sigma away from the mean, it's kind of huge. And for the second component, kind of represent the size, the width of the face, and the third and fourth. And for the textures, we also have the average texture for the shape. For the first principal component, we have kind of color of the, or darkness of the texture. For the second, I don't know how to interpret it, because this is learned unsupervisedly. It might not fit like our interpolation or our semantics over the faces. Okay, so let's talk about the properties of the two like linear models. So we're gonna discuss the 4 properties: linearity, interpretability, orthogonality, and constraints. So for linearity, I would say both models are linear. Okay, just a linear combination of the static poses to create new poses. And in terms of interpretability, because blend shapes are created for specific reasons, they are mapped to a semantics like mouth open, jaw opening. However, for 3D movable model, it's unsupervisedly learned. It's kind of hard to interpret those principal components. So let's say we have this as our first principal component. This is our second. It's actually hard to say, okay, this is angry, this is sad, and this is, I don't know, you name it, okay? And in terms of orthogonality, because 3D movable model is a process of principal components. where all the principal eigenvectors are orthogonal to each other. So it's guaranteed like a blend shape, a parametric model like 3D morpho model is orthogonal. Okay, the first component is orthogonal to the second, while the second is, and the first is orthogonal to the third. But for blend shape models, I don't think it's orthogonal because you can have a mouth open, but you can also have a mouth smiling. And I believe they are not orthogonal. And it turns out that for blend shape models, you can have like duplicate blend shapes. It doesn't matter because for an animation, most blend shape values are actually 0. It's actually a sparse array where most of the only a few like blend shape weights are activated. In terms of constraints, I would say blend shapes are more constrained because if we have all the blend shape like weights activated, it turns out that it looks like this. Every blend shape weight is activated and you try to blend between all the exaggerated expressions, and the vertices, the meshes kind of break down. So this is another reason why we say, okay, blend shape animations are sparse animation curves. Because if you activate too many like weights, the meshes, the textures will break down. Okay, some of the pros and cons using the parametric face model. The advantage is that it has low dimensional control space and it's linear, so it's easy to use. For blend shape values, for blend shape faces, it has the semantics, so it's kind of a very good tool for visualization or interactive editing. And another important property is that for a 3D morpho model, even though no matter how you change the blend shape weights, a valid face is guaranteed. Okay, it can be larger, it can be smaller, but it's a face. So look at the example right here. These linear parametric models prevents us from editing, like wrongly editing some vertices that makes an invalid face. And for the disadvantages, there are constraints for blend shape models like this. Because it's linear, when we view it from the opposite direction, the variety is limited by the defined control space. So let's say you would like to build a 3D morpho model, but you only invite a few people to join and scan their face. You don't have much variety of the face identities and the positions. It turns out that you cannot approximate your 3D morpho model to anybody because you only have like only a few characters. Another important thing is that for blend shape models, like these blend shapes, these semantics might overlap. So let's say I would like a mouth open while a mouth smile. It's kind of hard because when the mouth opens, when the mouth smiles, it opens. So if both are activated at the same time, the mouth will be too large. And that's why some manual, like checking, manual fine-tuning is required for animation production. And even with these plane-shaped semantics, it's still laborious to create such a facial animation, especially on faces. It takes like 79 to 90% of the time to do keyframing, to do smooth interpolation. So let's talk about the applications using the parametric face model. So one of the interesting property with regard to parametric face model is that it's valid face guaranteed. So that means no matter how you change the weights, you still got a face. So we're going to use this property for face reconstruction. The task of face reconstruction is given as follows. You have a face image. We would like to reconstruct its 3D face, even the textures, the colors, the poses, the orientation, and some of the details. And in order to do this, we actually need like landmark detections, face detections. We need morpho model fitting, like wrinkle synthesis. And these tasks can be used for expression transfer, expression retargeting, facial animation synthesis. We will only talk about like the morpho model fitting and their applications. Okay, so how can we reconstruct the face from a monocular RGB image? So given the face that looks like this, we would like to find the morpho model weights, or we say parameters, such that the reprojection of the 3D face into attempt to the image is similar to our original image. So we call this by an analysis by synthesis process. In order to synthesize something, in order to find the parameters, we first synthesize something and analyze it, get the difference between something we synthesized and between the something we synthesized and the ground truth. We get the feedback, back propagate to change the parameters. So to do this, we can start by randomly initialize the alpha, beta, gamma. The alpha refers to the identity morpho model. The beta refers to the expression. The gamma refers to the texture. And through a camera projection, you can actually set up the camera positions or the orientations of the face. And you can also add some lighting conditions, like you have a directional light, and the positions and orientations of that light is also a parameter you need to optimize. And through the camera projection, you can get a face like this. And from the face, you can compare this face image with the original input face image. Okay, so if some of the like textures or colors does not fit, we define the difference in the energy function and kind of back propagate to fine tune the alpha, beta, and gamma. So the energy function can be defined as follows. It's called energy, but I would say it's the difference between the two images. So we're gonna minimize that difference. And energy function can be defined as a energy dense feature alignment and sparse feature alignment, and some of the regulations over the alpha, beta, gamma parameters. So, and we also have weights that kind of balance between them. Let's say if we think like the dense feature alignment is more important than the sparse and the regularization term, we can increase the weight dense. So dense feature alignments are actually like pixel colors. So you can directly compare the per pixel error between the ground truth image and the synthesized image. For sparse feature alignments, you are given two images. You can use a third party like landmark detection to detect the landmark for each image and compare the positions of difference in positions of the two images of the landmarks. The regularization terms limits the parameters and avoids distorted faces. So, wait a minute. So these alpha, beta, gamma is usually because we have too many energy terms to optimize. So very easily, this optimization will fail because of overfitting. So it's important we use a regularization term to kind of limit the alpha, beta, gamma, such that alpha is kind of between 0 and 1 or -1 and 1, and beta is kind of close to 0. That's something we want. Instead of some alpha value that is like 1,000 and another beta value that is kind of -100. That's something we would like to avoid. Okay, the image formulation, I'm going to skip this. Okay, so let's look at some results from previous study. Given an image here in the upper row, we can first reconstruct the faces using a morphable model. In the middle row, you can see that the face orientations, the expressions are mostly covered in the morphable model. And beyond that, based on the result we have from the morphable model, we can try to predict the textures, the wrinkle details from the morphable model. So it's kind of a two-step process, two-step reconstruction. The first step, you use analysis by synthesis. You try to fit the morphable model to this face. And the second step, you try to add details onto that model such that it fits the original image. Another work from 2016 basically does the same thing. It started by first detected the facial landmarks and the face regions, use a multi-scale like reconstruction process. A core scale is the morphable model. From the morphable model, it tries to add more details to the medium scale and fine scale. And the extension from previous work is that once it has the ability to find the blend shape values, it can re-render these morphable models with textures to generate a new 3D outputs, even though this face expression is not seen in the original data set. So you can also look at the details, the wrinkles around the eyes. the coarse scale, and the refinement. It looks actually good, very good. Okay, so there are other applications using morpho models and facial reconstructions, because with facial reconstructions, you are able to convert a 2D thing to a 3D thing. And if you set up a camera with proper rendering techniques, you can kind of convert the 3D object to a 2D image. So because we're using the 3D morpho model, once we reconstruct the original image to a 3D face model, we can kind of tweak the blend shift values in the 3D area and create a new expressions, render to image to create a new image. So applications include these expression transfer, So for example, if we're talking about expression transfer, we say that we have an image source and a character, a blend shift character, like with several blend shift, because it's a digital character, it has to use blend shape. And once we have the original face as input, we reconstruct its face. Once this is reconstructed, we have the morpho model, the weights for the morpho model, and those principal components will be mapped in advance to the blend shapes of these digital characters, so that you can kind of do expression transfer or have your digital character do the same expression as your input source. And it turns out that this approach can be done on the fly, not just offline, because you already have those like the mapping between principal components and the blend shape of the digital characters. Okay, we can also like convert from one image to another image. So let's say we have a source image, which is reconstructed by a facial reconstruction. We have the alpha source, we have the beta source. We can kind of, beta is the expression. We can replace the source image's expression with the target's expression and do re-render, so that the target face has the same expression as the source image. And of course, you can do the other way around if you are able to convert a 3D morpho model to different like face identities in the image space. Okay, this is the same thing. I'll just skip it. Okay, so another application is the audio-driven animation. Once we know how to represent our faces, we can kind of map these blend shapes to like similar components in the audio. So in order to animate a lip syncing, we have phonemes in the field of audio. We have visons, which is visual phonemes, in the field of like visual counterparts. So let's say the phoneme is the mouth is mapped to the mouth wide open vison. So you can think of a vison as a pre-created blend shape that has a mouth wide open. So if we have a phoneme in the audio that is we can immediately map it to this blend shape with specific weights, let's say 1 or 0.8. And the phoneme MBP can be mapped to mouth closed. So actually it's a many-to-one mapping between the phonemes and visomes. And the task of audio-driven facial animation is to generate these talking face animations that match the input audio, the content of the input audio. And some of the remaining issues are like the speech. It has lots of informations. It has the contents, the visomes, the emotions, the prosody, the tones, even the speakers. So it's important you kind of filter out the unnecessary informations and leaves the contents alone. And from these contents, we map it to the visomes, to the bend shapes. So you can think of, okay, we can do like speech reconstruction, convert the speech to the text or to the visome, to the phonemes. From the phonemes, we do a text-driven animation to map it to the phonemes. And another important thing is the co-articulation effects. So when we humans speak, we don't speak phoneme after phoneme. So let's say when we pronounce hat, the hat, it's actually a 3-phoneme word, at. We just pronounce hat, not at. Okay, so that's the effect of co-articulation, because once we get the phonemes, the 3 phonemes, we have to try to blend the phonemes together or blend the visomes together to kind of create such an co-articulation effect. Okay, so another important thing is that once we have a face model, let's say we have a morphable model, usually the identity remains unchanged while we only change the expressions, and these expression parameters are controlled by speech, or you can map it to the phonemes. So one work from 2017 tries to map the windows of phonemes to the lower face vertices, and it requires the speech recognition process that converts the speech to the text to the phonemes, and it uses a sliding window. Okay, window size of 5 frames, I believe, and the neural network model that tries to map the phonemes into the animation curves from the data set it collects. And it turns out that these animation curves, face representations, can be retargeted to a different character with some of the predefined rig mapping, the band shape mapping. Okay, so another work from 2018 tries to do it end-to-end. Like in modern worlds, we prefer end-to-end things. Previously, we need a speech recognition module before we can do these content mapping, the facial animation synthesis. But here we directly start from the audio features, the raw audio features, using convolution-based neural network model that converts a window of audio features into like a sequence of vertex positions, a static frame, and it also has a unsupervised learnable emotional latent code that can be used to control the style of the talking face style. one of the interesting property with regard to this work is that since it's using the raw audio features, not speech recognition process, it's actually generalized to different languages. This means that when you train this model on only English data set, you can apply this model to a different language as input, and it still faithfully generates the output, the faces, the animations that match your input. So it's actually a surprising thing. And the face representation of this work is the raw face vertices. And they claim that it only needs 3 to 5 minutes of data to train this. So it's actually pretty powerful. Recently we have a production based on this work from NVIDIA. It's called Omniverse Audio to Face, if you have heard of that. It's the same as this. So we have like about 10 minutes left. I'm going to introduce our latest work. This is called Disentangling Audio Content and Emotions with Adaptive Instance Normalization for Expressive Facial Animation Synthesis. So our task is defined as follows. Given an audio and any specified emotion, okay, we would like to generate facial animations that match the content of the audio, which is the phonemes, the voicemes, and the expressions that must match the specified emotion. So it's kind of, we separate the emotion as a new modality and use it as input to control the expressions of our output animation. This is kind of useful because previously we use only the audio itself to try to generate the facial expressive faces. But it turns out that the previous works usually can only learn the mappings between the audio contents and the voicemes. For the expressiveness, most of the output animations are neutral. And think of this in the context of a conversational agent where you try to do a text-to-speech, you have a dialogue management, generates a text for a response for an embodied chatbot. From the text response, you would like to synthesize speech. So, and from the synthetic speech, from the text-to-speech engine, you're gonna like generate facial animations for that character. But since we are using the synthetic speech, not the real speech, the synthetic speech is usually neutral, emotionless. And that's a problem because once you are relying on the audio emotions to give you the information on the expressiveness of your output animation, but once this input is emotionless, you cannot generate expressive animations. So that's why we try to do this. And we call this emotion conditioning because such a model has to learn the emotions from a specified emotion while the content from the audio. So some of the limitations from prior work, like the first prior work, usually only focus on mappings between the contents, not the expressions. The second one is able to generate kind of expressive animations, but it's kind of hard to control the expressions. Either it's angry or it's happy, partly because their emotional latent code is not supervisedly learned. And this is our approach. We're gonna start by an audio-visual data set. We have the audio, angry audio, the angry emotion labels. We have the videos, a sequence of images, frames that is expressive. We do a facial reconstruction from the images to generate the textures and the face vertices, which are multiple model based. And from the audio and the labels, we put it here, use as input to train our entire model. And we would like the entire model to output vertices and textures such that the vertex movements, the lower face movements, matches the content of the audio input, while the expressions, mostly the expressions here and the textures, match the emotion input, the specified emotion. So we start with a bidirectional audio encoder because we are trying to model the intra-frame dependencies. So we use bidirectional recurrent neural network, and the output of the audio features and the embeddings of the emotion input is passed to a module called adaptive instance normalization. And at this stage, we would like to wipe out the time invariant information from the audio, which we assume is the emotion from the audio. Because emotion, we assume that emotion persists during the whole audio sequence. And what is left alone is the audio content. With the audio content, we try to combine the remaining audio content with the embeddings from the specified emotion. And those joint embeddings are passed to a decoder, which is also bidirectional recurrent neural network. And we kind of try to visualize this joint content, audio content, and specified emotion embedding as here. I'll show you later. And after that, we use a linear model, a linear layer to generate vertices, which is 12,000 times 3 dimensional. And from the joint content emotion embedding, we use a texture generator, which is convolution-based, 2D convolution-based, to generate textures. And from the vertices and textures, we combine them in a 3D game engine to create the final animation. Another interesting property is that we actually use textures on top of the facial multiple models. This is because when we start to reconstruct the faces from the expressive video data set, it turns out that if the input is an angry face, this is the reconstructed face in core scale, which is the multiple model alone. And it looks kind of neutral compared to this one, because the 3D multiple model is just an approximation of the face vertices. It does not cover the details, the wrinkles. So that's why we, on top of these multiple model layer, we add textures on top of it and try to find the details inside so that we can tell, okay, this is a happy face and this is an angry face. And for the optimization, since our output, the output of our model has vertex, positions, has texture, images, we kind of do like mean square error between the vertices and the textures. And we also add the constraint on the velocities, which is the intra-frame like differences. This is because it prevents the model from predicting something that is over smoothed. And we kind of borrowed this idea from one previous work in 2018. And it turns out that it helps speed up our optimization process. So we optimize with 3 losses. And this is our result, the emotion conditioning. The first row are using angry audio as input, the second happy, neutral, sad. But we will wipe out the emotions in the audio, but try to add the specified emotions to the final facial animation so that, look at the first column, it matches the angry, every column matches the content. We have happy faces, regardless of which emotional audio is used as input. This is something we want. And we also visualize the joint embedding. We can see that this is a TSNE visualization. We can see that, okay, this is happy, and this is, okay, this is fear, and this is surprise. Geometrically, surprise is close to fear, which may not be consistent with our perception. And this is neutral. Well, this is, what is this? Oh, this is neutral is close to sad. Geometrically, disgust is kind of close to angry. Well, this is aligned with our perception, disgust and angry. Angry and disgust looks pretty similar. Okay, in terms of evaluations, we have 2 objective metrics. We report the average vertex error and the average pixel error. And once we are trying to evaluate emotion conditioning, the specified emotion would be different from the audio emotion. And we don't have such data with like those different emotions. So we conduct a user study. We generate for any emotion or for any audio, we generate the 8 emotional outputs. And we ask the users, okay, given this animation, please categorize this animation into one of the 8 emotions. And it turns out that our result kind of beat most of the previous works in terms of the emotion conditioning. But in terms of texture error, the MedStar is an image-based approach with the reconstruction. It has the best quality, but it cannot do like emotion conditioning. And we also report the confusion matrix of the ground truth and the prediction. And it's obvious that, okay, happy is mostly predicted correct. So along these diagonal, these are correct, accurate predictions. Well, you can see that, okay, disgust is confused with angry. Okay, it's also interesting because we see that from the joint content emotion embedding that their embeddings are close to each other. So it's kind of interesting. While fear is kind of close to neutral, probably because fear is kind of hard to model. Okay, another user study, we asked the question, okay, given the animation from one work and the animation from our work, which do you prefer in terms of animation quality? So it's actually an A-B test. You choose A or you choose B. So it turns out that ours beats all the others in terms of animation quality. And we also compare our works with a model that is without adaptive instance normalization. And ours is slightly better than this ablation study. Okay, so finally, this is the last slide. I'm going to present the animation results.
One even gave my little dog a biscuit. The revolution.
The audio is on. I assume you cannot hear the audio, right?
Now underway, and materials handling makes this much easier.
Because it's coming from my laptop. How could I? Let me see. Oh, what about this?
It was not whatever tail
Not working.
was told by Tails. No, the man was not drunk. He wondered how he got tied up with a stranger. No, the man was not drunk. He wondered how he got tied up with a stranger. No price is too high when true love is at stake.
This is recorded on Zoom.
No price is too high when true love is at stake.
No price is too high when true love is at stake. No price is too high when true love is at stake. No price is too high when true love is at stake. No price is too high when true love is at stake. No price is too high when true love is at stake. No price is too high when true love is at stake. No price is too high when true love is at stake. No, the man was not drunk. He wondered how he got tied up with the stranger. No, the man was not drunk. He wondered how he got tied up with the stranger. No price is too high when true love is at stake. No price is too high when true love is at stake.
Okay, so that wraps up today's presentation. Thank you for listening. So what are we going to do next? I was told that some of you need to come up and present your progress.
I guess we usually just do the kind of, we don't really come up with like the actual, but yeah, we usually give like updates and stuff.
Okay, so who wants to come up? Or your
Should we do it in order or?
yeah, I don't know. This is my first time here.
Alright, well, I guess, so our project is, like the word differentiation, so we're trying to create a model that,
Wait, would you like to come up and share your screen?
oh, we don't have like a power.
Oh, okay,
It's just like, we just give it. So yeah, our model, we're basically trying to take like, input and then we're trying to decide